Now I'm going to talk about the main theorem of this section, the subdifferential sum rule. Let me go ahead and state the theorem and give the detailed proof. Let f1 and f2 be extended real valued convex functions. And we suppose the following condition. Suppose that this intersection, this is the intersection of the relative interior of the domain of the function f1 and the relative interior of the domain of the function f2 is non-empty. Roughly speaking, this condition means that the domain of the first function intersect the domain of the second function significantly. Then we obtain the subdifferential sum rule. That means we have the following. Then the subdifferential of f1 plus f2 at x bar is equal to the sum of the subdifferential of f1 and x bar at x bar and the subdifferential of the function f2 at x bar. This is true for all x bar in the intersection of the domain of two functions. Okay. So in this formula, the left hand side is a set and the right hand side here is the sum of two sets. So the sum of two sets is the set of all possible sums v1 plus v2, where v1 belongs to the first set and v2 belongs to the second set. Okay. Let me also point out a particular case where this condition is satisfied and therefore we always have this subdifferential sum rule. Okay, so in the case where f1 and f2 are real value functions, okay, and they are convex functions, then the domain of the first function is Rn and the domain of the second function is also Rn. Okay, so the relative interior of the domain of the first function is also Rn, and the relative interior of the domain of the second function is also Rn. So the intersection is Rn, which is non-empty. Therefore, this condition is always satisfied, and so we have the subdifferential sum rule. So for two convex functions with real values, without any condition, we have this subdifferential sum rule. So this is a very, very nice and useful result. And let me go ahead and give the detailed proof of this theorem. The proof is rather involved. Now let me go ahead and give the detailed proof of the main theorem. Let us first prove the following. The subdifferential of f1 plus f2 at x bar is a subset of the sum of the subdifferential of f1 at x bar and the subdifferential of f2 at x bar. Okay, so this is rather involved. And the proof is based on the normal cone intersection rule for convex sets. So let me fix any v in the subdifferential of f1 plus f2 at x bar. Then we will show that v can be represented as the sum of v1 and v2, where v1 belongs to the first subdifferential here and V2 belongs to the second subdifferential. Okay, so by the definition, the inner product of V and x minus x bar is always less than or equal to f1 of x plus f2 of x minus f1 of x bar minus f2 of x bar, and this is true for all x in Rn. Okay. So to continue the proof, we're gonna define the following sets. Define omega 1 is the set of all x lambda 1 and lambda 2. This element is in Rn times R times R, or in Rn plus 2. Over here, lambda 1 is greater than or equal to f1 of x. So if we look carefully at the definition of omega 1, we will see that omega 1 is the Cartesian product of epigraph of f1 and R. Okay? And similarly, the set omega 2 is defined by x lambda 1 lambda 2 in Rn times R, where lambda 2 is greater than or equal to f2 of x. Okay? And in order to continue, I'm gonna separate the proof into several steps. Okay? So in the first step, with the definition of omega 1 and omega 2 here, we will show that the following is satisfied. V minus 1 belongs to the normal cone to the set, the intersection of omega 1 and omega 2 at this point, x bar, f1 x bar, f2 x bar. Okay, so let me prove this based on the definition of the normal cone to convex sets and also the structures of omega 1 and omega 2. Okay, so how come this is true? We fix any x lambda 1 and lambda 2 in the intersection of omega 1 and omega 2. Okay? By the definition, this element belongs to omega 1 and omega 2. Thus, we have the following. Lambda 1 is greater than or equal to f1 of x. And also, lambda 2 is greater than or equal to f2 of x. Okay? And then we have the following. If we compute the following inner product. V minus 1, and here x lambda 1, lambda 2 minus x bar, f1 x bar, f2 x bar. This is equal to the following. The inner product of V and x minus x bar minus lambda 1 minus f1 x bar, and then minus lambda 2 minus f2 x bar. Okay? And because of these conditions, lambda 1 is greater than or equal to f1 of x, and lambda 1 is greater than or equal to f1 of x, and lambda 2 is greater than or equal to f2 of x, this is less than or equal to this inner product, v and x minus x bar minus f1x of x minus f1 of x bar minus f2 of x minus f2 of x bar. Okay? Now, because v is in the subdifferential of the sum of f1 and f2, then this inequality is satisfied. Okay? So now if we arrange this inequality by moving the terms on the right hand side to the left hand side, we have exactly this. And therefore, this is always less than or equal to 0. Okay? So the inner product of v minus 1 and x lambda 1 lambda 2 x bar f1 x bar f2 x bar is always less than or equal to 0 whenever we take x lambda 1 lambda 2 in the intersection of omega 1 and omega 2. So by the definition of the normal cone to convex sets, we have exactly this. Okay, so I already completed the proof of the first step. In the second step, I'm going to show that the intersection of the relative interior of omega 1 and the relative interior of omega 2 is always non-empty. Okay, so this condition is required in order to apply the normal cone intersection rule for omega 1 and omega 2. How come this is true? Let me go ahead and look at the definition of omega 1 and omega 2. From the structures of omega 1 and omega 2, we have the following. The relative interior of omega 1 is equal to the relative interior of the epigraph of f1 times the relative interior of R. So this is the Cartesian product of the relative interior of the epigraph of f1 and the relative interior of R. Okay? And this is just the relative interior of the epigraph of f1 times R, because R here is the whole space R, so the relative interior is just itself. Okay, now this one can be written as follows. This is the set of all x lambda 1 lambda 2 in Rn times R such that x is in the relative interior of the domain of f1 and lambda 1 is strictly greater than f1 of x, and here lambda 2 is arbitrary in R. So we obtain this formula because we already talked about the representation of the relative interior of the epigraph of a convex function presented earlier. Okay, and similarly, we see that the relative interior of omega 2 is the set of all x lambda 1 lambda 2 in Rn times R such that x belongs to the relative interior of the domain of f2, and here lambda 2 is strictly greater than f2 of x. Okay, and note that we have the following condition. This is the assumption of our theorem. The relative interior of the domain of the first function intersects the relative interior of the domain of the second function. So we can fix an element z in this intersection. Okay, so we fix z that is in the intersection, in this intersection, relative interior of the domain of the first function, and here relative interior of the domain of the second function. Okay, so now if we look at this representation for the relative interior of omega 1, we see the following. This element z, if we take here f1 of z, for example, we add 1, and then here f2 of z plus 1. Okay, then here is lambda 1, here is lambda 2, because z here belongs to the relative interior of the domain of f1, and this element lambda 1 is strictly greater than f1 of z, and lambda 2 here is arbitrary, so this one belongs to the relative interior of omega 1. Okay, and similarly here, this element z belongs to the relative interior of the domain of f2, and lambda 2 here is strictly greater than f2 of z, because it's f2 of z plus 1. Okay, so this element also belongs to the relative interior of omega 2. So we have completed the proof of the second step, that is the intersection of the relative interior of omega 1 and the relative interior of omega 2 is non-empty, where omega 1 is defined by this formula and omega 2 is defined by this formula. Now let me finish the proof of this inclusion by applying the normal cone intersection rule in the third step. Okay, in the first step we saw that v minus 1 belongs to the normal cone to the intersection of omega 1 and omega 2 at this point, x bar, f1 x bar, f2 x bar. And in the second step, we know that the relative interior, the intersection of the relative interior of omega 1 and the relative interior of omega 2 is non-empty. So we can apply the normal cone intersection rule that is written here. The normal cone to the intersection of omega 1 and omega 2 at x bar is the sum of the normal cone to omega 1 at x bar and the normal cone to omega 2 at x bar. Okay, so let me go ahead and write down the formula. So this is equal to the normal cone to the set omega 1 at this point. Okay, now at this step we're gonna apply the formula in order to represent the normal cone to omega 1 at x bar, f1 x bar, f2 x bar. Okay, note that omega 1 is the Cartesian product of the AB graph of f1 and r. Okay, and if we take an element lambda in r and we compute the normal cone to r at lambda, then this is just 0 because the normal cone to the whole space at a point in that space is always 0. We already proved it before because lambda here always belongs to the interior of R. So then the third component in this normal cone is 0. Okay? And similarly, the second component in this normal cone is 0. So we have the following. This is equal to, so then we have the following. Then V minus 1 can be written as follows. V1 and then the second component in this normal cone, so I can write it as minus gamma 1, okay, and then the third component is 0, okay. Here this is V2 0 and minus gamma 2, okay. And over here, because of the structure of omega 1, we have the following, where V1 minus gamma 1 belongs to the normal cone to the AB graph of the first function at x1 fx1. Okay, and over here V2 minus gamma 2 belongs to the normal cone to the epigraph of the second function at this point. Okay, so then we have the following. Then V can be written as V1 plus V2 because of this equation. V is equal to V1 plus V2. And then we also have that minus gamma 1 is equal to minus 1. So gamma 1 is equal to 1. And gamma 2 is also equal to 1. Okay? Now, we have the following. Since V1 minus 1 belongs to the normal cone to the epigraph of F1 at this point, by the proposition presented at the beginning of the lecture, V1 belongs to the subdifferential of F1 at x bar. Similarly, because V2, gamma 2 here is 1, so V2 minus 1 belongs to this normal cone, we can apply the same proposition and have that V2 belongs to the subdifferential of F2 at x bar. So, therefore, the element V can be written as the sum of V1 plus V2 and V2, where V1 belongs to the first subdifferential and V2 belongs to the second subdifferential. Therefore, we have proved this inclusion. Okay. Now, the remaining part of the proof is the following. We have to show that the sum of the subdifferential of f1 at x bar and f2 at x bar is a subset of the subdifferential of the sum function. Okay. However, this proof is very, very easy. Okay, I'm going to give you a hint of the proof of this theorem, of this part, and then we can prove as an exercise. So now to show that this is true, we will take V1 in here and V2 in here. Okay, then by the definition of the subdifferential, we always have that V1 x minus x bar is less than or equal to f1 of x minus f1 of x bar. This is true for all x in Rn. And similarly, because of this condition, we have that V2 x minus x bar is less than f2 of x minus f2 of x bar for all x. Okay. And now, if we add these inequalities, we have the following: V1 plus V2. This is x minus x bar is less than or equal to f1 plus f2 of x minus f1 plus f2 of x bar, and this is true for all x in Rn. Okay, therefore V1 plus V2 belongs to the subdifferential of the sum function at x bar, and the proof is complete.